All right. Hi, everyone. I'm Han from BOScoin, and we flew all the way from South Korea to meet you guys. So thank you for having us here. We're really excited to be able to come outside of Korea and really talk about what we've been working on outside our own country. And hopefully you'll find some things that you'll find interesting, and maybe we can talk about some of those parts afterwards. Right, so let me just introduce you to our team, first of all. So our CEO is actually a fintech entrepreneur in South Korea, and he founded the largest financial information services in Korea, called Paxnet, and he's also one of the co-founders of Blockchain OS. Our CTO, who's also with us today, can you say hi? And he's basically the architect for the BOScoin platform. And so if you have any technical questions, you can ask him afterwards as well. And then there's me, the COO. You could just call me Han. And I used to work as a application developer in South Korea for banks. And recently I've come over to the Blockchain OS team and started working as a consensus developer. Also here with us today is actually Ash. Say hi, Ash. He's the one that's been asking all the difficult questions today. And he's been advising the BOScoin team for about a year now. And so he's incredibly knowledgeable about the blockchain space. So he's also someone you might want to talk to. So I'll go straight into the overview. So we're going to be talking about three basic things. So what exactly are we building? Who should be running it? And how will we grow it? Yeah? So what are we building exactly? We're actually building smart contracts, again, right? So as you all probably know, smart contracts are programs that enforce themselves. They run themselves, right? But we're doing it slightly differently. We're calling them trust contracts, and that's not the only thing that's different. Our trust contracts are programs that we can prove they can enforce themselves. So I guess you're going to start asking things like, why is that important, right? Why is it important that contracts can provably run themselves? Well, last year, I'm sure you've all heard about the $50 million DAO incident, right? So the DAO is basically one of Ethereum's largest projects. Well, it wasn't until it broke, but the DAO basically stands for Decentralized Autonomous Organizations. And so what they wanted to do was they wanted to codify all the rules and decision-making processes onto smart contracts and have organizations run decentralized on the network. And so people love the idea, and they raised loads of money. They raised almost $150 million. It was the largest crowdfunding event up till then, but it was hacked, right? $50 million worth of Ether were withdrawn, right? And the reason that happened was because of a simple coding error, the recursive call error. And basically that's kind of a problem that happens quite often in programming in general. Like software developers make mistakes, right? So we asked ourselves, how can we stop this kind of thing from happening again? Well, first of all, we kind of looked at what Ethereum is made up of. Ethereum is actually a Turing-complete language. It creates smart contracts on top of a Turing-complete virtual machine, which basically means that you can program anything you can think of onto the blockchain. So if you can program anything you want onto a blockchain, it basically means you can even program things that are logically impossible onto the blockchain. And so Ethereum's approach is basically to provide developers with as much freedom as possible. But we ask, at what cost, right? The approach that Ethereum uses with smart contracts basically means that after somebody writes a contract, you need to audit it and see if it's okay. And then you also have to look for bugs, things like recursive call errors, before the contracts are called or uploaded. So what we did is basically we took a slightly different approach. We decided to create a Turing incomplete programming language. But instead of it being just incomplete, we made it decidable. So in computer science, decidable basically means that when you run the program always results in true or false. So it doesn't result in maybes, it doesn't result in I don't knows, or it doesn't get lost, basically. It always has to turn out to be true or false. And that's something that could only be done when you get rid of the Turing completeness. Right? So what happens when you start creating contracts that are decidable? It basically means that the contracts can never have unknown consequences. They're always right or wrong. And secondly, we can know beforehand how it'll run, right? So you don't actually have to pre-audit the contracts. We can actually pre-audit the contracts automatically before they're uploaded onto the blockchain. So by starting from a completely different architecture, we believe that this kind of structure can actually prevent accidents like the DAO from happening beforehand. Now, the second issue with the DAO. So after we know why the DAO happened, what were the legal implications? So an interesting perspective of the DAO was that the DAO wasn't a hack at all, right? I'm sure you've heard of things like code is law. The person that exploited the code, or the hacker, can claim that if you take away his codes, or if you take away his coins, it's actually an interference with his right to the coins that he created. All he did was use the code. However, at BOScoin, we don't really think that code is law, at least smart contracts anyway. Because looking at the legal definition of a contract, in English common law, it usually goes, a legal contract is a mutual agreement between two parties, right? And then there's the tiny bit that goes under that. It also means that each party must have the capacity to enter a contract. Now, when you run a smart contract, there's usually three parties, right? There's the developers, the participants, and the executor. And with smart contracts, and especially during the DAO, the developers didn't have the capacity to understand the contract, the participants didn't understand the contract, and maybe even the virtual machine didn't understand the contract. So what we wanted to do was we wanted to build trust contracts that were closer to actual law, right? And the way we wanted to do that is by improving the capacity to understand the contract that they're entering. So for developers, we chose a decidable language so we can decrease the room for error. We improve the readability of trust contracts so they can make decisions themselves. So our contracts are actually much more human readable than what smart contracts look like. And they're pre-auditable. So the VM can actually know, well, we don't have a VM, but on the blockchain, when you run the trust contracts, they can know how long they'll run beforehand. So I mean, when Bitcoin first came into the world, what they really did was they allowed people to move away from trusting banks, right? And Ethereum, when they came along, they gave us a whole bunch of freedom. But at the end of the day, when you look at smart contracts, what you're doing is you're putting your trust in the people that created these smart contracts, right? And what we want to do is we want to return that trust back to the people that actually do the signatures, right? The people that are participating in the actual smart contracts. So hopefully, our trust contracts, since they're specifically designed so that people as well as the programmers can read the code and interpret them the same way, hopefully this will improve the literacy of the contracts on blockchains as a whole. So to summarize, what trust contracts are they're provably executable contracts on the blockchain, readable by both humans and computers. So I said trust contracts are basically made up of two languages. It's made up of the web ontology language OWL and the timed autonomous language TAL. So this is a bit of sample code that we wrote up. And one of the largest differences is basically, if you look at smart contracts, the data as well as the logic, it's all written in one script, right? But what we did is we basically divided the data aspect of the contract and the logic aspect of the contract. And so the data is described using the OWL language, which is a semantic language. And then the logic is divided into another script called tal script. What this division basically does is it improves readability, and it's also a very common programming pattern, I guess, because it's, I guess a lot of people just call it data-driven development. And we structured our trust contracts so that we can clearly see where the data is and where the logic is. Now, I'm sure some people might know what web ontologies are. Sorry. But this is basically what a web ontology language looks like, right? So this is how we describe data on trust contracts. And this particular data is actually a set of data about crowdfunding. So you'll see things like funders and funding and interest rates and everything that's involved with crowdfunding. But the reason we use OWL to describe data is because of the structure of how it's because of how they structure their data. Basically, the structure of ontological languages is usually done in triples. So they use things like objects, attributes, and relations. And using those three sets is basically how they can describe any kind of knowledge that we've picked up over the years. And not only is it described in this way, basically our ontologies are actually shared. So once somebody creates intelligent data, is what they also call it, anybody can use this kind of data set in their trust contracts as well. So the more and more trust contracts you create, you're actually adding to the reservoir of knowledge that's on top of the blockchain. Right. Now the second part is the timed automata language. This is actually a language that we created within our company. Timed automata is actually quite an old theory, but applying it to blockchain technologies is actually quite new. And one of the first features that it does is it does operations, right? So I said in the sample code above, there's OWL that describes the data, and tal that describes the logic. And so one of the first features that it does is it does operations, so like adding and subtracting the data. So that's how we mold the data into the output we want. Secondly, what it does is it limits operations through time, right? So if we look at, I'm going to compare this to Ethereum in a bit. So what you can do is you can model operations through tools like the ones on the left as well by using these, using time as a limitation. And because we're using a decidable language, we can pre-calculate how long every combination of logic within a trust contract would take. So why is time important? When you give people the ability to create programs on the blockchain, not only do you give them the ability to express anything they want, you also provide them with the power of process spamming your network. So this is something that happened quite often. Like in a lot of times, Ethereum is actually spammed by these kinds of transactions. And basically what they do is they create really complex or infinitely looping contracts with the intention of overwhelming the network. So what Ethereum did was they constrained this kind of activity by having the contract consume a limited resource for each operation. And that limited resource is basically gas, right? And gas comes from Ether, the currency. So what Ethereum is doing is they're using an economic model to limit DDoS attacks on the network. But what if the value of the attack is greater than gas? The economically rational being would attack the network until marginal gains from the attack is equal to the marginal cost of the attack. And so they'll just keep on attacking and attacking and attacking until they stop them, right? And that's what happened with the DAO attack as well. The marginal cost it took to run the malicious code was actually way, way lower than how much coins they could create through the hack. Now, what BOScoin does is it just uses time. So all we do is we see how long the contracts will run beforehand, and if it takes too long, we'll stop it. That's how simple it is. So, I mean, economic models are really important. I mean, that's why Bitcoin took off in the beginning as well, right? But applying a secondary economic incentive model to the processing power only complicates things. Because gas is also used for transaction fees, miners want to make, miners will try to only put smart contracts that have high gas rates, and users will only want cheap contracts. So there's a bit of a conflict of interest in that aspect as well. So, so that's basically why BOScoin uses a timed automata model rather than an economic incentive model. So I kept on talking about TAL and OWL a lot, and not a lot about BOScoin. And so this picture is basically how it fits together. The TAL and the OWL language actually sits on top of OWL chain, the protocol layer. And that's completely separate to the coin layer, which is also referred to as the platform layer. So everything regarding the issuance of the coin, as well as remittances, and we also have a governance feature, that kind of thing, they all lie on top of the platform layer. And all those functions are actually written in OWL and TAL. So they're written in the trust contract language. So on to the next part. Who should be running these decentralized systems? So I'm sure everybody knows about the Bitcoin blockchain debate, and I'm sure everybody's heard too much about it, right? But again, we thought there should be a way to solve this, right? And we thought the reason these problems just don't go away is because of these 4 things, right? Bitcoin doesn't know who should be making the decisions. Should it be the exchange providers? Should it be the people that have the most Bitcoins? Or should it be the developers? Nobody really decided who should be the ones that should make the decisions. Additionally, nobody knows where they should make the decisions. There's no like single place that people should go to make decisions. And then there are the rules. Should it be more than 50%? Should it be more than 70%? And then lastly, even though they develop something, like such as SegWit, there's no real way to force people to get onto the new updates. So what we decided to do is to make some decisions. We said, the people that make the decisions are going to be the stakeholders. So for BOScoin, the people that are the stakeholders are the node operators. They have to put some stake into a node for them to be a stakeholder, and they get 1 vote for that. Secondly, where do you make decisions? We actually embedded the governance system into the BOScoin platform. So you can vote within the system. Thirdly, what are the rules? The rules are actually all defined within the trust contract. So whether there should be a majority vote or a 60% vote, or how long the vote should take, like all this information is actually defined within trust contracts. And thirdly, how do we implement change? We have automated updates. So automatically, after you decide on a rule, these updates can be implemented. So this is how a basic proposal works. We actually have 2 different types of proposals, one that asks for money and one that wants to change the system. And so for a basic proposal, it's actually quite similar to Dash. What you do is you write a proposal, and then you upload it onto the blockchain, and then the node operators have a vote. And if that proposal is passed, the amount that they asked is sent to the person that put up the proposal. So it's pretty simple. The system proposal is a bit more interesting. So as I said, all the rules within BOScoin are written in trust contracts. And so all the rules that are written in trust contracts can also be updated according to proposals. So for instance, if you wanted to raise the transaction fees for BOScoin from 0.1 BOS to 0.2 BOS, what you could do is you could update the code yourself. You could update the trust contract that used to say BOS transactions are 0.1 BOS, and you could update that to say now they're 0.2 BOSes. And obviously that won't be implemented automatically. It would have to go through a vote. So after you upload the proposal onto the governance network, people will vote once again, like before. But this time, when it's passed, we assume that the network has a consensus on the updated information. So what happens is that the trust contract itself that everybody's referring to is updated, and everybody on the network updates all together. So this is a feature that automates the updated features within a decentralized network. Right. And lastly, so how will we grow? You know, there's a lot of currencies that come out every single year, and it's the same for Bitcoin almost. I mean, I know all of you here are really enthusiastic about it, but growth is still something really hard to kickstart. And I guess one of the reasons is because it's always like, should the chicken or the egg come first? I mean, if you're on a currency, you need both sellers and buyers. And sellers won't come until there's buyers, and buyers won't come until there's sellers. So what we decided to do is we're going to kickstart our own platform. We've actually developed a couple of applications, and this one is just one of them. It's actually a prediction market for celebrities, and we're actually using some of the commons budget that we have issued from within the issuance schedule to develop these kinds of consumer-facing applications to get people onboarded. Right. So we've been developing this product for over a year now, and we're almost up to the testnet date. That's at the end of this month, and then in the middle of April we'll be having our first ICO. Which you guys can all participate in if you want to. And then we have our Genesis block launch, which is on the 30th of June. And then we'll be launching our iPhone and Android wallet specifications in our Nebula block. So hopefully things will go to plan. And that's basically a wrap for BOScoin. Thank you very much.
Just one question quickly. So you mentioned that instead of gas, you use time, but then, I mean, presumably different types of transactions would take different amounts of time. Does that mean they cost different amounts, or I didn't quite understand what that actually means when you say time.
Right. So at the moment, we don't have different prices for I guess very complex trust contracts and like simple trust contracts. At the moment, all transaction costs are fixed at 0.1 BOS, and all we're assuring to the network is that all contracts will either succeed or fail within a set amount of time. That's all we're promising to the network.
So who's the ideal user for you?
I guess so we're a public blockchain. So anybody can really create nodes and participate in the governance system. So what we really want is to get average users to get really involved in this kind of technology as well. And that's why we have things like consumer-facing applications as well, and like things like smart contracts as well. They're not going to be written in a programming language. They're going to actually look very similar to legal contracts as well. And so hopefully people that can basically read will also be able to participate in creating trust contracts. I don't think you'll be able to see the code because it's actually quite small. We don't have any large ones at the moment. So no, not today, sorry.
So you said there's going to be a pool of trust contracts that are going to be developed as the platform progresses, and then when I develop a trust contract, it's going to be added to the pool, and at the end you're going to have a set of awesome pools that people can trust contracts that people can choose from?
Yeah, that's
Okay, and you build using these trust contracts, you can build dApps, as Ethereum calls it, or?
yeah. Decentralized apps are on the milestone, and yeah, decentralized apps are obviously on the milestone, but the applications we're creating right now are actually separate from the blockchain. But in the future, yeah, definitely, like decentralized applications is definitely somewhere we want to go.
Okay, lots of questions.
So, cool presentation, thank you. In the logic side, you still have a state machine that has its own state, sequential circuit, and so limiting by time is interesting. But at the end of the day, I'm wondering what sort of guarantees are you able to provide, and how does this compare to work in Ethereum, for example, with formal verification? At the end of the day, you're still dealing with a state machine, and you've got many challenges there. So I'm just looking for the differentiation.
질문을 내가 정확히 모르겠는데 지금 그 타임드 오토마타에 대한 설명을 원하는 것 같은데 맞나요?
So, could you clarify your question just a little bit? As in, what's the difference between Ethereum and using Tau?
So at the core, it's not a combinational logic circuit, it's sequential, so it has state, right? And you're proposing, the problem is the halting problem, right? So when does this thing stop? Ethereum stops it with simply saying you've run out of gas, right? You're saying let's stop it based on it's run out of time. That's the core. But you can do a lot in a second, right? At 1 megahertz, you've done 1 million operations, right? So I guess I'm confused as to is that the essence of the difference? Is it simply time versus gas? And does this get to the heart of addressing the halting problem, maybe? And related to this too, so that's part one. Maybe you follow? Yes? Okay. So, and part two is, one thing that you can sort of get at is simply how in circuit land they got at it with formal verification, right, for smaller circuits. This is the path Ethereum is going down, where you're saying, okay, I can cover all these states in this space over this period of time, and you can actually formally prove it. And so that's how Ethereum is going down this path to solve it. And I'm wondering if, as Ethereum rolls out formal verification, it might reduce the delta. So what is the answer to that? And I like the path. I'm just curious.
Okay.
It's a nerdy question. I'm sorry.
지금까지 질문이 뭐였는데?
그러니까 뭐 시간이라는 개념으로 너무 막 쉽게 해결했다.
아니 그게 아니고 타임드 오토마타는 그 인피니티 오토마타를 그 피니티 오토마타로 전환하는 기술이에요. 그러니까 지금 보면 핵심 기술이 뭐냐면 버추얼 머신이 이제 그 지금 튜링 컴플릿 머신을 시간 제한을 줘서
environment. And so obviously Ethereum has to go down the path of reducing errors that can be caused due to Turing completeness. But we're just starting with a slightly smaller scope. And hopefully, I guess at the end of the day, it really depends on who has fewer hacks. And I think only time will tell from that perspective. Yeah.
Okay, well, let's.
I will just like to add an opinion on it. I've been running Ethereum community in Korea for 2 years, and like there's been so many things problematic around Ethereum, and is to take like many discussions. I will happily do that. And for Ethereum, like you mentioned, there's a gas to stop like infinite looping. Like there's a language like looping language for while code, and yeah, like it boosts the efficiency. But the Ethereum way to stop abusing it is just put the gas process, right? So once you run out the gas, it stops. The problem is the attacker is able to keep processing the gas. You just need to pay. So just recently, as recently happened in Ethereum memory pools and their transactions, you just need to pay because it's cheap. Why it's cheap? Because to platform to go process and platform goes boost its ecosystem, it must be cheap. Fee must be cheap, right? So many platforms and many applications on top work on itself, and many people can join. If the fee is too expensive, like ecosystem wouldn't work, right? So that's why they put cheap gas price and fee price. But it's kind of contradictory, I think, because to stop the attacker, it should be expensive. It's too cheap for attackers. So why don't you separate the two contradictory factors? So why don't you put just time on attacker side and maintain the cheap price on the platform side? So if you put a time and if you can predict how long the code takes, then the miners can choose, the validators can choose if they want to run this time of the code or not. So they get to choose and still maintain the low fee price. That's how it works, I think.
Cool, very interesting. Okay, well, thanks so much, guys.